So in a previous video, I talked about trigonometric ratios, and I drew, a picture of a right-angled triangle with angle theta, side lengths A, B, and C. And we talked about how trigonometric ratios, like, for example, the tangent of theta is just given by B divided by A. And the cosine of theta is given by adjacent over hypotenuse A divided by C. And so on for the common trigonometric ratios. Now, a question that was left on the table in that video was, why does this work? Right? This is a particular triangle that I drew with particular side lengths A, B, and C. What if I drew a bigger or a smaller triangle and I kept the angle the same? How do I know that the ratios of the side lengths would stay the same? So that's what I'm going to establish in this video. I'm going to say, what if I have two right angle triangles and they both have angle theta in one of the non-right angles. One of the non-right angle angles is theta. So let me take this to be, for example, the smaller one, and then draw a bigger version of this triangle, also with angle theta, which means I can draw it, I can overlay it on top of this triangle, like this. So it's still a right angle triangle, it still has angle theta here, and it's just bigger. There's a smaller one and a bigger one. So I'll call this extra distance here A prime, I'll call this extra distance up here C prime, and I want the extra distance, so I'm going to draw a dotted line, right angle, sort of making a right angle with this line across, so that this is B, and this extra distance here is B prime. So what we want to show is that the ratios of the length of the sides in the small triangle are the same as the ratios of the corresponding sides in the big triangle. So for example, for tangent, we want to show that B over A, opposite over adjacent, is equal to B plus B prime over A plus A prime. And we also want to show for cosine that A over C is equal to A plus A prime over C plus C prime. And finally, B over C is equal to B plus B prime over C plus C prime. This is our goal. And actually, this picture that I drew already has a hint of how to prove these three equalities using very elementary geometric arguments. Okay? Because the total area of the big triangle can be calculated in two ways. I can calculate its area simply as a triangle, in which case it's half of a rectangle, so it's equal to half the length of this side, A plus A prime, times the length of this side, B plus B prime. But another way of calculating this same area is by observing that it's made up of three subregions: a triangle, another triangle, and a rectangle. This triangle has area 1/2 AB. This triangle has area 1/2 A prime B prime. And this rectangle has area A prime B. So I've just written the area of the big triangle in two different ways. And I can use this equation, so I can multiply this out to get 1/2 AB plus 1/2 AB prime plus 1/2 A prime B plus 1/2 A prime B prime equals 1/2 AB plus 1/2 A prime B prime plus A prime B. Now I've got my AB and my AB, both half. I've got my half A prime B prime and half A prime B prime. This A prime B, if I subtract this half A prime B, gives me, on this side, 1/2 A prime B, and on the left-hand side, this one's left over 1/2 AB prime. So maybe somewhat surprisingly, by writing the area in two different ways, I get a non-trivial equation. This is an a times b prime, and this is an a prime times b. And so if I rearrange that, what I get is, what's the most convenient way for me to rearrange this? I think I want to write it as b prime divided by b equals a prime divided by a. Okay, that's just by multiplying both sides by 2 and then dividing both sides by a times b. And this is useful because I can manipulate it a little bit further to say that because these are equal, I also know that b prime over b plus 1 is equal to a prime over a plus 1. Which seems like a silly thing to do, except that tells me, by finding a common denominator, that b prime plus b over b is equal to a prime plus a over a. In other words, the proportion of how much longer is this b plus b prime side compared to the original length of the b side is the same proportion as how much longer the a plus a prime side is compared to just the a side. Now, if you have our three equations in mind as our goal, this immediately gives us one of those three equations. By rearranging from this, we get b prime plus b divided by a prime plus a equals b divided by a. So we get this one. But we can also use this to get the other two by making the following observation. Let's call this x. So let's call this proportional. How much bigger is the side of the big triangle than the side of the small triangle, comparing the same side? Let's call it x. So what we get is that, what this tells us then, is that b prime plus b is equal to b times x. X is how much times bigger the longer side is. And similarly, a prime plus a, the length of the longer adjacent side, is equal to ax, the length of the smaller adjacent side times this multiplying factor. Now why is that useful? Because we can use the Pythagorean theorem on this big triangle to write a plus a prime squared plus b prime squared equals c plus c prime squared. But a plus a prime is just ax squared equals, plus bx squared equals c plus c prime squared. Now factoring out the x gives me x squared times a squared plus b squared equals c plus c prime squared. That's just factoring out this x squared. And now I can use the Pythagorean theorem again. A squared plus b squared equals c squared to get x squared times c squared equals c plus c prime squared, which means xc equals c plus c prime, which means x equals c plus c prime divided by c. So what have we realized here? We've realized that this ratio, this common ratio, that if you multiply the b side by x, you get the b prime plus b, and if you multiply the a side by x, you get the a prime plus a side. It also applies to the hypotenuse side. So we also have that, for example, running in a space here, we also have that c plus c prime over c is equal to x, which is equal to b plus b prime over b. Which we can again rearrange to get b over c equals b plus b prime over c plus c prime, which is exactly this one. And if I use the fact that c plus c prime over c is also equal to a plus a prime over a, I can get this one in exactly the same way. So with a little bit of elementary reasoning, right, we draw this diagram, we calculate the area in two ways, and we get these corresponding ratios. We dip our toes into the Pythagorean theorem a little bit. we can derive the fact that these three ratios don't depend on how big or small you draw the triangle. They just depend on the fact that it's a right angle triangle and that the angle over here is theta.